You see the PowerPoint?
Yes, yes.
Okay. Yeah, let me get started then. And if others join, they will join in the next, it will be very introductory. So
Okay.
hi, everyone. My name is Elif Tokar Erdemir. I'm from Quantum Computing, QCI. And I joined QCI in September of last year. My background, as I mentioned to Dong Yang, is in operations research. So I got my PhD from Buffalo, New York, University at Buffalo. And then I did a postdoc at the University of Minnesota. And I worked on a few other companies before joining to QCI, where I did more on optimization modeling in retail and healthcare. And after joining QCI, I think my role here is, we have this quantum solver, a solver that can solve optimization problems in quantum machines or classically. And we work with a variety of customers to take their problems and formulate it for them and transform it for quantum machines and then send it to our solver. So that's the part that you will see today. This presentation will be more like a 101 on operations research, where you will see how to mathematically model real life story problems and how we can also solve these problems in Catalyst. So that's going to be the focus of my talk. And that's, I think, where QCI is also trying to add value to quantum business, to bridge that gap of adding the business value and solving problems with quantum machines. So I will first start with some modeling framework for constraint optimization problems and give you some examples of the applications you will see in real life industry. And then I will move on to the components of those that mathematical model, which are decision variables, objective function, and constraints mainly. And then I will move on to one example that we will all work through together on formulating it. And that's a class scheduling problem. And I hope it's a familiar problem that as students that you face, that when you're picking your classes, that are, what are the variables in that problem? How do we think of the objective function, the constraints that come into play? And then how do we set up that problem in Python and send it to Catalyst and understand expected results? So that we can also, I will show you, not with a live demo today, but I will hope to show you a script in my presentation on how do you submit that problem to Catalyst and what are the results you will get back. And what do we do to submit it to a classical or the quantum solver? Okay, so optimization models. So when we think of these business problems, the first thing that comes to mind is, what is the decision that we are making, right? So that the first thing that we think of is the decision variables. And here I say the user wants to make some decisions. And in my mind, the user is either you as the person who wants to solve this problem, or it can be the business person, the subject matter expert in the business side who wants to come up with the decisions for their business challenge, right? So they want to make some decisions. They are called decision variables in the framework. And when making those decisions, the user also has some value in their mind that they want to optimize. And that's the objective function of the optimization problem. But you cannot optimize it unless you meet certain criteria. So there are some restrictions or rules in the user's mind that they cannot, violate or exceed. They need to meet those conditions. And those are called constraints in the constraint optimization model framework. And some of these can be bounds on the decision variables as well. And the last part of the framework is when the user wants to make this decision, they have some data in their hand, right? So they want to use this data and they analyze the data that will help to come up with the best decision. And that's called input parameters. So these four components get together and then they make up the mathematical model formulation. and where we minimize or maximize the objective function subject to the constraints. And these objective and constraints are expressed in terms of the input parameters and the decision variables that we define. So starting with this, now I want to show you multiple examples from like applications that will fit into this framework. And first one is a simple problem. It's the knapsack problem. Maybe some of you heard of it, but it's knapsack is the backpack. And you have a backpack, you will travel. And what you want to do is your decision is you want to select items to put in your backpack. And that's your decision variables. But in choosing among all the possible items, you want to maximize the value of the items that will go into the backpack. And that's your objective in your mind. And then your backpack cannot fit more than a certain set limit of items. And let's call this the weight limit, right? So you know the weight of the items. So you don't want to exceed that. And that's the constraints. And then you know the weights and the values associated with each of those items. And those are your input variables, input parameters, actually, that you come into this framework with. Another example can be the assignment problem. Assignment problem is also very common and it shows up in many different applications. So here you can think of you have some jobs and then you have some machines and you want to assign these jobs to the machines. That's your decision. And you're trying to decide on which jobs should be assigned to which machines. And when making that assignment, you may want to minimize your cost, right? So you want to keep the assignment cost as low as possible. That's your objective. And then maybe you are restricted with a one-to-one assignment. Like each machine can only do one job. So you need to maintain that one-to-one assignment, and that can be the constraint. And you know the cost of assigning each job to each machine. So that's the cost data that you have, right? That's the input parameter. So those are the four main things for this problem to know before mathematically modeling it. Another example is the facility location problem. That's again, maybe there are so many, there's a retailer. They want to open up new shops and they want to know which locations they need to locate the new facilities. It can be pharmacies, it can be distribution centers, it can be clinics, right? So that applies to many different application domains. And you want to know where to open those among potential sites. And then when doing that, the objective in your mind is I want to minimize my cost of setting up these facilities and shipping costs to the customers from those locations. So that's your objective function. And you want to make sure that all the customer demand you identified in your area that you will serve will be covered by the facilities that you open. And then maybe there's some capacity of the facilities, and maybe there are certain number of facilities you cannot exceed because you have some budget, right? That those are all the constraints that are applicable. And then you can the setup costs, capacities, shipping costs to each customer, the demand. These are all the data that you know upfront to solve this problem. Another one that actually we are also dealing with some of our customers is a set partitioning problem. So the name may not resonate like what it means, but it is usually used in crew scheduling or airline scheduling problems or route planning. So you want to select routes to assign crew members, for example, and which routes I should be going with as an airline company. And we want to minimize the total cost of covering the selected routes. So that's the objective function in our mind. And then among all the possible routes, I want to make sure that all my origin destination pairs will show up in exactly one route so that I don't duplicate, I don't assign two planes to the same route, to the same origin destination, but I also make sure that it only shows up, all of those are covered. There's at least one plane, right? Going from destination A to destination B. And then we know the costs and the list of the origin destination pairs upfront. So that's the problem framework for this set partitioning. And I promise this is the last one. This is again a well-known one. This is the traveling salesperson problem. And that's another tough problem to solve. And this is in optimization model framework where we want to build a route for a traveler. And let's say here in the picture, you see all the cities, like the capitals of the states. But the traveler wants to visit all of these states, but they want to minimize the total traveling time or cost of the trip, right? So that's the objective function. And each city should be visited only once, and the person must return back to the starting point. So these are the constraints for this problem. And you know the time that it takes from going from city A to city B, and that's your data input parameter to solve this traveling salesperson problem. Okay, so after, I think now we have an idea on what are the various types of problems that optimization can show up. And it's in many different areas in our lives, right? So, and I mentioned the framework, but the first thing in the framework, as you remember, it was the decision variables. So the decision variables can have mainly three types. One is the binary variables that I will get back to this because that's going to be our main focus. It's a yes or no. So we either choose or not choose a certain, decision, make it or not, right? So that's the binary nature. For example, is a particular task assigned to this machine at time t? The answer is a yes or no. So that's a binary variable. And integer variables are, they take their whole numbers, they take integer values, and they can have lower or upper limits. For example, how many bags of rice needs to be transported to a oil drilling platform today? So that's a whole number. And continuous variables is the other one, and that's the real value variables, right? So these are, again, they can take decimal points, they have upper or lower limits if you want. For example, I'm trying to build a portfolio of assets for my financial portfolio, and I want to decide on what should be the proportion of this specific asset to show up in my portfolio. That's a financial portfolio optimization problem, and this variable is a continuous variable. So in my talk, I will focus on the binary variables because continuous variables, for example, they are handled very well with classical computers, but not well by digital quantum computers. And quantum machines, as of today, they are composed of quantum bits. They are binaries, and they are called qubits. And integer variables can also be represented in terms of binary variables, but in order to express those, we will need many qubits. So it's easier to tackle the problems that have binary decisions with quantum machines. There's always a transformation for the others, but I think for today, let's focus on the binary variables. And in the next few years, we believe there will be attempts to offer integer variables as part of quantum computing. I mentioned briefly, but let's think about a couple other examples of binary variables. In scheduling airplanes, right? So we may ask, does plane P use gate G at time T? And we may represent it with that mathematical term, XPGT, which will take 1 if the plane is really using gate G at time T, and it will be 0 otherwise. And same thing in traveling salesperson problem, where we may say, does the person visit this house H on stop S of the trip? And that's a yes or no question. And we may represent it with an XHS. That's a binary representation. Or in robot optimization, or we may call it like a task allocation in the warehouses to robots, we may say, am I going to give this job J at time T to my robot R? Or it can be a warehouse worker, right? So it doesn't, so that's another binary variable. We may call it XRJT. Or for the first problem I showed you, which was the easiest, I think I shouldn't say easiest, but easier, I think some preliminary example of optimization, knapsack problem. So does this item I go into the backpack or not? That's an XI. You may call it an XI variable, which will take value of 1 if we select to put the item in the backpack, and it will take a value of 0 if not, right? So that's the framework for binary variables. And once we have the decision variables in our mind, we can move on to, for example, constraints as next, or it can be the objective function, but let's start with the constraints. As I said, constraints are the requirements or the rules in the user's mind, and we need to comply with them. Like those are, if a user comes with those constraints, they are usually hard constraints in their mind, that they, like a budget constraint. They may be flexible with how you put that constraint in your model, but we usually start by thinking this is a must, this is needed for the user. And we try to express those also mathematically in our mathematical model. But first, starting with the English terms of, in words, expressing the constraint helps before jumping into the mathematical formulation. And there are two constraint types I will distinguish here because that's important for the quantum modeling. So equality constraints and inequality constraints, right? So some constraints may take equality form. So you have this combination of your decision variables and they are equal to some number. And in inequality constraints, your combination of decision variables may be either less than, greater than, or less than or equal to, greater than or equal to some number. And in quantum machines, we need to transform our problems with inequality constraints to equality. But I will focus on that a little more later. So again, giving you some examples, other than just saying that it's a combination of the variables. For scheduling airplanes example, right? So we say, for example, no more than one plane may use gate G at time T. That's an inequality constraint, and I will show you why. Or traveling salesperson problem, when we say exactly one house can be visited on stop S of the tour, that's an equality constraint. And in assignment problem, when we say machine M can do at most one job at time T, that's an inequality constraint. And you may get it from like, I'm sorry. Like when we say no more than or at most, those are inequalities. Or when we say exactly this number, that's an equality. So getting into the next slide, I will show you, I think, how mathematically that's an inequality or equality. So for the scheduling airplanes example, when we say no more than one plane can use gate G at time T, what that is when we define that as a binary variable, whether the plane P is at gate G at time T, we basically sum over all the planes for gate G and time T, and then say that the summation should be less than or equal to 1, because only one, at most one, plane can be at gate G at time T. So that's the summation. That's basically the mathematical representation of this constraint. And we have to repeat this constraint for all the gates and all the time periods, if that's what we want. And traveling salesperson, when we say house H can only be one of the stops, like we don't want to come back to the same location, right? So every stop will be visited once. So for house H, if our variable is house H in stop S, we basically sum over all the possible stops. And that's number of cities actually. And that should be equal to 1. So only one of those stops will be valid for house H. And in assignment problem, when we say machine M can do at most one job at time T, we basically change the job index here. So machine M, it can be either the job, first job, second job, third job, so on at time T. And that's the summation across all the possible jobs. And that should be less than or equal to 1 in this constraint. And please feel free to interrupt me if you have any questions, like if something doesn't make sense or if you want to hear more, let me know. So the next thing is the objective function. An objective function is the goal of the optimization. And after formulating decision variables, constraints, the objective function usually simpler to consider. And it's expressed in terms of the decision variables and input parameters. And we want to minimize or maximize that quantity. So for traveling salesperson, I said we can minimize the total mileage traveled. For robots task allocation, it can be minimizing the downtime or maximizing the packages put into the boxes. For planes, choosing landing gates, maybe it is minimizing passenger wait times or minimizing the distance that each plane needs to travel to get to its gate. So there can be many different criteria in mind to minimize or maximize. So what does it actually, it's good to know at the higher level, but are there any restrictions in our constraints and objective function formats for quantum machines? I think right away, the easy problems will be like for objective function, there are some limitations to be able to solve by quantum machines. And that usually takes the desired format is usually the quadratic format. And what I mean by that is we can have linear terms in our objective function, just like you see here. So you have the coefficients and then the variables coming in, or you may have quadratic terms where you have the multiplication of your binary variables. But you cannot have higher order or division in your objective function to submit it to a quantum machine. We need to do some transformation to get it back to a linear and quadratic term only format. And for our constraints, actually with solving with Catalyst, it can only include linear terms. So we won't have the quadratic terms in our constraints. But there's a transformation. Like if your problem has a quadratic term, it doesn't mean that we can not ever solve it with quantum machines. It just needs some transformation. But right away, this is the desired format for objective and constraints. And let's work on an example. And that's the story problem I mentioned. And that's the class scheduling problem. So before jumping into the class scheduling problem, any questions from you guys? I'm happy to answer.
So I have a quick question. I wonder, in terms of complexity, which example will be the most complex? Is it the traveling salesman's problem or is the set partition problem?
Oh yeah, that's a great question. I think all of these, Dongyang, they are all NP-hard problems. They are all complex. And it's hard to say which one or the other because it will also depend on the size of the problem, the input data that will come into it. And there are some, like even though they are NP-hard, some of these problems can be solved with classical computers today. And sometimes, some instances take longer or less for some other easier versions. And people have also some other algorithms or heuristic methods in mind to solve those problems. So I cannot easily say that this one always be more complex than the other, but they are all in the NP-hard category.
Okay, gotcha.
Yeah, but that's a great question. Yeah, I think as we work more and more on those problems, we realize that usually, the complexity, it's not easy to tackle. And as you increase, for example, traveling salesman, as you increase your number of cities, it will definitely get more complex. Either it will take longer to solve, or you may not even solve it with classical computers if you exceed, I don't know, thousands of cities, for example. But I don't have those numbers right out of my mind, and it's but these are all fun problems to think of. You know, if you cannot solve it with a solver, how do you tackle it? Like, what are the best ways or heuristic approaches that you can develop? So there's a lot of literature on each of those problems. Yeah. Mhm. So this class scheduling problem, it's something I think we encounter, and scheduling problems are also in general harder problems, but this is a very custom problem that we developed just for this webinar. And it is more to see that, you know, what are the different types of constraints we may see in a problem? How do we express our objective function? And this is something I think you all face in your you know, scheduling or selecting your classes for your college studies, right? So the objective, for example, we chose is you may have some idea that which class you like more and which class you like to be registered more than the others. And let's call this your eagerness score for this problem. And then you have some, of course, requirements by your department. And that can be some general education requirements, like you need to get a 1 math class, 1 Spanish class, 1 science class, for example, and maybe that's more applicable to high school. And then there are also time slots, right, that each class is offered, and you cannot take more than 1 class in the same time period, right? So even though that's something, you know, intuitively, that's not possible. And then you have some major requirements. For example, you need to get all the required courses in operations research during your studies. And then there may be some paired classes, like there's a lecture and then there's a lab that goes with that lecture. And you want to make sure that you get both of them. So you cannot, otherwise it's not going to be allowed to take just the lab or just the lecture. And we know the eagerness score for each of the classes. So it may not be quite visible, but what I will do is I will share this problem and the data with you guys after this webinar, so you can play with it. But for now, you will get an Excel file like this that will have the classes, and then I have the variable name for each class. And then you see the times that each class is offered, and whether the class requirement is a major or English or math, it's also shown in here. And then you see which class is paired with which other class, and the scores, right? Eagerness scores are also on this Excel file. And on the side, you see how many of each class category you need to get, like 2 major classes, 1 English, 1 major, and that's it. And in the Excel file, I will also give you other constraints. So you will get to think of, you know, what it means to really solve this class scheduling problem. So now we know the data that's available to us. So what is our binary variable, or what is our decision variable here? Right, so we can define the decision as whether the student will take this class or not, right? So I showed you that there are 20 classes here, and then each class may get 1 variable, like class 1 gets an x1, and then x1 can take the value of 1 if the student will take that class, and it may take the value of 0 if the student won't take it, right? So we have 20 of these variables. Each variable is for each of each one of the 20 classes. And given those binary variables, the 20 binary variables, we can build our objective function as the total eagerness score. So let's call EI here as our eagerness value. And then we have 20 EIs, right? So that because we have 20 classes. So we can express our objective function like this. So it's this, we multiply EI by XI, and then we just sum over the 20 courses. And if this class is selected, let's say class 1 is selected, it will take the value of 1. it means its eagerness value will be counted as part of our objective. And if it is not selected, we will just not count the eagerness. And we want to maximize this value, right? And maybe the maximum is if we take all the 20 classes, but we know we cannot do that because of our constraints. So now I'm going to move on to the constraints piece so that we will see what are the restrictions. And like I said, the time period is the first one, right? So we can only take one class in a given time slot. So for example, classes 14 and 17, they are part of the same time period. So only one of those, or at most one of those, actually, we can choose, because maybe we won't take any course in that time period. So that's the constraint that we define. And the other one is the pairing constraint. So we can either select none or both of the paired classes. So classes 1 and 17 are paired. So their value should be the same. So when one is 0, the other one should be 0. And one is 1, the other one should be 1. Another constraint is our major constraint, right? So we must have 2 classes in the operations research category, for example. And there are 6 classes that are, let's say, qualified for operations research. And we have to have at least exactly, so in this case, exactly 2 courses from that group of 6 classes. And then among all the pairings, we say we can only have 1 pairing. So we only take one of the pairings in our schedule. But these are only examples, but we need to really repeat all the constraints in our mathematical formulation, which actually will end up with a formulation like this. So it's kind of small, but that's the entire mathematical representation for this class scheduling problem. And I think when you get the Excel file, it will be, I think, helpful to check back with this formulation so that you see if you're formulating the problem correctly. So here on top, we have the objective function, which is maximizing total eagerness of selected classes. And there are 20 terms here. So we are just multiplying eagerness score with the variable, and we are summing across all of them. Subject to this first set of constraints are the time slot related constraints. There are, let's see, 1, 2, 3, 4, 5, 6, 7 available time periods. And then for each time period, we just say we can take at most one of the courses. And then the next set of constraints are the major or the specialty class requirements. And finally, the last set of constraints here. So there are actually 1, 2, 3, 4, 5 constraints here. They are separated by commas because of the space. But there are 5 pairings in the Excel sheet. And we say we either take none of the courses in a pairing or both of them. So that's basically the full formulation. And if you remember what I told you, this is only binaries. So this is good for quantum machine. So we don't need any transformation of integers or continuous variables. But there are some inequality constraints, only this set. So rest of it is fine. They're all equalities. But when we see these inequality constraints, what we need to do is we transform the inequality to an equality representation. And what do we do for that? There are different ways, but for this specific problem, it's kind of easier. We just add one more binary variable to each of the constraints. And binary variables take 0 or 1, and our right-hand side values are 1. So that will be sufficient. So when, for example, in this first equation, if x14 and x17 are both 0, our slack variable, this is I call the slack variable, it will take the value of 1. And if at least one of those are 1, then our slack will be 0. So we maintain still, it's not a loss in our solution space. We just represent the same thing by adding more variables to the problem and transforming it to the equality format. Okay, so now we have the full formulation. And we need to get ready for solving this problem with Catalyst. And like I said, if we had integer variables, we need to do that transformation. We already transformed the inequality to equality. And by the way, so in the upcoming versions of Catalyst, we will be able to do that transformation underneath. So we don't, as a user, you won't have to worry about the inequality to equality transformation upfront. But that should still happen underneath because of the quantum machine needing the equality representation. So now we have the full formulation. We did all the transformations. So what does Catalyst do after that? So I'm going to get into how do you submit it to Catalyst. But before that, I think this is critical to know. So Catalyst minimizes or maximizes that mathematical combination of constraints and objective function. And that's called QUBO format. So Catalyst takes the constrained optimization and turns it into an unconstrained problem representation by adding these parameters called Lagrange parameters, or they are called constraint penalty parameters, into the final equation. And that becomes the final mathematical representation to minimize or maximize with Catalyst. And why do we need these penalty parameters? Because we still want to satisfy our constraints. That's, like I said, that's needed for the user. And if the constraints are not satisfied, this penalizes the final function, right? So it will get a larger value, for example. So we don't want our objective function, this final transformed objective function, to get high values, for example, if we are minimizing. So we will try to satisfy the constraints. So when constraints are satisfied, this term will become 0. But if it's not satisfied, then Lagrange parameters will show up. And because they are positive values, it will get your objective function value to a larger value, which is not desirable. So in Catalyst, as you submit problems, I think you all have access to it now. It's also called alpha parameter. So it can be just one value that applies to all the constraints, or you can define it as a vector where it's a separate value for each constraint. So you can give basically a different value for each different penalty for each of your constraints. But the simplest to start with, you can just start with one value of your penalty parameter and pass that into Catalyst. But we need to be really careful when solving real life problems. Like if this penalty parameter is too small, then it may look like okay to violate the constraints, because that final mathematical representation, it may get a higher value in your original objective function by sacrificing some of your constraints, but that's not what we want. We just want feasible. I call it, when constraints are satisfied, we call it feasible solutions. So we want feasible solutions. So we don't want this penalty to be too small. But when we also make it too large, then it means the violating constraints is becoming your dominant objective in the new representation. So your real objective function value may look like so small. It's like an epsilon effect on your final formulation. So we need to find somewhere in the middle, and it's found by trial and error usually. But as a first guess, either you can choose like the maximum coefficient in your objective function value as a trial, but it may not work if like all the coefficients are ones. So you may also choose it as like, oh, what is the largest value my objective function can take? So that these two terms, your objective and your penalized constraints, are comparable because we are adding them in that final unconstrained representation. So now we talked about the constraints, the objective function, and what is needed for Catalyst and what's happening underneath. I'm not going to go into these couple slides because I realized you all have, I think, have access to Catalyst and be able to set up your computers to use it. But this is basically just going over what is needed, like a configuration file. You need to have Python. you need to express your objective and constraints as matrices. So instead of these system requirements, let me move on to the expressing the objective function as a matrix. So let's assume you have this example objective function with our binary variables. How do we turn this into a matrix that's in desired format for Catalyst? What we need is we need to create a square matrix of the size of square of number of our binary variables. So we have 4 variables here, x1 through x4. So our objective matrix should have a 4 by 4 size. And it also need to have that symmetric format. So what I mean by that is like these terms, the just linear terms becomes the diagonal entries in that square matrix. But when we have the quadratic terms like x1 times x2, x2 times x3, these will be split into the 2 values, because in the square representation, we have a place for x1 and x2, and we have a place for x2 times x1, right? So we basically split 3 into 2, and we say 1.5 x1, x2, and 1.5 x2, x1. And we do the same for this term, where it is x2, x3, and then x3, x2. And that shows up in a matrix form like this. So let's look at x2 and x3. It takes 2 here, and then it takes the 2 here. And then x1 and x2 is taking 1.5 and 1.5 here. So this is just to maintain that symmetric structure so that we are not losing the, the representation of our objective function. So the diagonal entries in here, like I said, they are the linear terms. But if you think of this is a quadratic representation. So we have an x1 square here actually. So why do we get the linear term coefficient -1 and put it as like it is the coefficient of my quadratic x1 square? And the reason is because we have binary variables. It's the nice property of having binary variables where the multiplication of the 2 binaries is actually the same as your binary variable. So if the variable takes the value of 1, its square is 1. If the variable takes the value of 0, its square is also 0. So that's what allows us to represent the objective function like this. And constraints, there is no quadratic representation, like I mentioned before. We have a row for each constraint. So let's consider these 2 constraints in our problem. And then we need a column for each variable though. So that's the trick. So even though, for example, this constraint, maybe I will move on to this slide so that it's bigger to show you the same thing. So the first constraint, for example, has 3 of the variables out of 4, but we still need a spot for our second variable, x2. And the coefficient of x2 will be 0, but the other ones have a coefficient of 1. So they are getting those coefficients. And second row is for the second constraint, which has only variables 1 and 2. And we capture the right-hand side of the constraint in a separate array. And right-hand sides are 1. And again, its size is number of constraints times 1, right? So we have 2 constraints and just 1 column for the right-hand side value. Okay, now we have the matrices ready, and we can just in Python just put it as a NumPy array as our constraints, right-hand side, objective function. And what we basically do is after that, we just send this objective constraint and right-hand side to Catalyst as objective constraint right-hand side goes in as inputs. And alpha is our penalty, constraint penalty parameter that I mentioned. So it has the value of 1 in this example, but we can increase it. We may try 100,000 without going too large. So it's something to play with. And we will get it as a result whether our solution is feasible or not to the original problem. And just one line, we submit this to Catalyst. And as you see, I never mentioned, other than needing binary variables or equality constraints, we don't need to know anything about quantum machines up to this point, right? So we can submit it to a quantum solver with just that mathematical modeling knowledge that we have. So that's the beauty of Catalyst in my mind. And we can print the results right after our submission. We can just print the results and see what is the solution vector looking like, what is the objective function value or energy, as we call. Energy is that QUBO, the unconstrained objective function. We call it energy value, or we can check our original objective function value too. So with that, now we had the class scheduling problem. We had its input, and expected results will be in the values of zeros and ones. So the solution vector that we will get from Catalyst will look like this, just bunch of zeros and ones. But we know which variable, like which value corresponds to which variable. So like this is what our x1, this is our x2, and these were our class variables, right? So for example, x3 is 1, meaning that, oh, in this solution, we decided to take class 3 and class 4, but not classes 1, 2, and 5, and so on. And hopefully this will give us the solution that's maximizing the eagerness. So the most optimal solution is actually this. This is what we should get back. And it has all these variables fixed with like classes 3 and 4 are our two major classes. Looks like we are complying with our specialty class requirements, and we have only one pair that we got, and we got both of those classes, but nothing like none of the courses that's part of a pair where only one of them is chosen and the other is not. So it looks correct to me, and you guys can check after I think I share the file and sample code and running yourself too. But we solved this classically, actually, in that previous example. So if we want to send this problem to, for example, D-Wave, which is one of the quantum like machines we have access to, we just change the sampler parameter in our submission to bracket D-Wave. And we add maybe one more line here because there's a warning that comes up. We just turn off that warning and see if we get the same results. And hopefully, if you try, you will get the same exact solution as we get. So nothing is changing other than what we send as the input sampler to our Catalyst API call. Okay, so I'm done actually with the class scheduling problem, and I want to wrap up my presentation. But any questions on the class scheduling problem or submission to Catalyst?
I have a question. It's not necessarily right about this specifically, but it's more talking about complexity of problems. How do you talk about the complexity of problems on a solver like this? Like, what is our input? Is it the size of these matrices that we're using to represent it? And does that affect the time it takes for the system to settle?
Yes, definitely, yeah. One dimension of complexity, I think one of the major is number of variables you are sending in to the solver. It definitely impacts the time it takes to solve the problem. But also, like, there are certain problems that even though the number of variables are small, it may still take much longer to solve. Like, there are open libraries out there that you will find it's just binary variables, but maybe it's just 1,000 binary variables, but none of the solvers out there was able to solve that problem so far. So it's like an open problem out there. But in general, like regardless of that, I think number of variables and number of constraints is a good measure of complexity. But given that, we also have that other metric that is very important, density of your input matrices. So when you combine your objective and constraints together, density meaning, how many of your variables are tied to each other or linked through the constraints together. So that becomes it harder to solve for the solver. It's again, after that combination, that objective function plus the penalty times constraint squared expression, how many non-zero elements you have in that final matrix format is, I think, one of the maybe best measures, like a proxy measure of complexity.
Okay, thank you.
You're welcome. But that's a great question. Yeah, it's something, it's definitely not easy to say immediately that this is going to be a hard or an easy problem. But density helps to know, variable count helps to know a little bit. But you may still end up getting frustrated, even if it doesn't look like easy. It doesn't look like hard at the beginning. But in general, like when we are starting, like I said, to summarize, start with defining your variables and then expressing your objective and constraints in terms of those variables. And write the full formulation. It helps either explicitly or with these summation terms, and then take it into the matrix format for Catalyst and see what the results are looking like. Try to interpret it in terms of your variable definitions and see if it makes sense. And you can also check in Catalyst whether that solution is feasible or not to the original problem. And you can go back and iterate. And actually also, getting started with a mathematical formulation is sometimes hard. That's why I think with our QBTU course book and materials, we started with very simple mathematical representations. So starting small is always good to get familiar with the solver, and then obtaining results and checking the solution, and then slowly increasing the problem size and see where we are struggling, right? Solving the problem with our solver, either with the runtime or finding a feasible solution or finding the best solution. And because also Catalyst, I should say that, and Quantum is probabilistic, you may want to try it a couple times, because every time you run it, you may end up with a slightly different solution, or sometimes it may be very different solutions, given if it's a big problem. So it helps to really get familiar with starting small and knowing what to expect. And let us know, like as you start looking into more and more problems with Catalyst, let us know of any issues that you will come across. And I will be sharing some homework problems that are more like real life problems, especially this class scheduling problem, as I told you, but route planning problem and job assignments after this call.
Hi, Alif. I have a question. First of all, great presentation. Thank you for this. I'm sure everyone has some great takeaways from this. So my question, I mean, while you were thinking, it's a bit more fundamental. While you guys were talking about, optimizing an objective function, right? And objective function here was the eagerness. My question is right now, is there a formalism, or is there a structure in which we can optimize perhaps multiple objective functions? Like I want to optimize eagerness as well as like something else, and I want to maximize both. I want a solution that is a trade-off. Maybe one would optimize one objective, another, but I want one that optimizes both. So is that a direction that we can think forward to?
Yeah, that's a great question, Hamza. It comes up a lot in optimization world too. You may want to minimize distance and also minimize cost. But I think one way is combining those in a single term, mathematical term for your objective function with some trade-off parameter, right? Like an example is what we are doing with constraints with the penalty parameter. You may think the same for your two different objective functions. Like you may maybe, but then we have to be really careful on what is that trade-off weight you will associate with each of the parts of the objective, right? Because one may be in dollars and the other one may be in time, right? So or some other units. So that becomes a challenge. And one other thing people do is maybe identify one of those as your primary objective and just use that as your objective function. But the secondary one goes like a constraint. Like you may want to minimize your cost, but you don't want to sacrifice your service level to your customers. So service level requirement may become a constraint. And then you may play with that, I want at least 95% satisfaction, and then solve it and then see what cost you get. And then do maybe some iterative format that you will feel comfortable as a user. Or maybe use service level as your primary and the other as a constraint. So
I
that's,
see, I see.
yeah.
And then whoa, I mean it's amazing. And then just top of my head, I think that maybe we could, have like you said, E1 times X1. Let's say E1 is eagerness. And if I want to maximize it, and minimize something else, could it be like E1 minus, B2, and B2 could be something else?
Yeah.
So I can maximize and minimize while having the same objective functions as long as I have those scaling, right?
Yes, exactly. And E1 and EIs and BIs are if they are in the similar units.
Yeah.
That makes
Yeah.
perfect sense. Yeah.
Oh,
But
I see.
if it is not like a dollar.
Obviously,
units.
apples and oranges. We can't compare them. It
Exactly.
has to be the same. Yeah.
Yeah.
Okay. Okay. Thank you. Thank you.
You're welcome.